And that that same kind of jump is what you do in quantum. You go from the Schrodinger equation, that stuff, and then you jump to the path of formulation.
That's exactly how the quantum block is going now. That class will be very dependent on the professor you get.
I was looking at it, so it was like physics 7,800 here. It was like quantum field theory 2 or something. And the notes are unintelligible.
Yeah, that's what
you just draw symbols and points arrows to things and you plan to go to grad school? Yeah, same year. And you're a third year.
I'm a second year.
Second year, okay. Second year. You're second year too, right? Yeah.
Okay, so I sent everybody an email this morning, mainly pairwise. So that just want to make sure that we individually cover slightly different material for our final presentation for those of you who may possibly overlap. But right, yes.
There's a question about the actual format. Do you want us to go about doing it on a slides presentation, or do you want us to go up there and right in the blackboard?
Completely your choice. So this is hopefully this experience will give you some pedagogical experience. What works best for you to communicate your ideas? That's really something you can't know without trying it out. Whatever appeals to you, if you haven't had much experience with that, give that a try. I find that personally, presenting mathematics is not very. There's some pathways, neural pathways that get copied by students when you actually write things on the board as they write things down. That's my experience personally, but I've seen plenty of valid new mathematics be presented via slides. I don't think I would choose to do that personally, but it's up to you. Right, so in addition to these emails that I sent, I also constructed a survey about the timing. I think informally I've talked with most of you if it would be okay if we used an extended version of the final exam slot that we were scheduled. Just want to decide when that would be, and also ask you what you'd like to eat on the day of the presentations. So if you haven't filled that out yet, please do, so I can know something. Okay, any questions in general about the end of the term? Oh yeah, I released problem set 4 finally this morning. Sorry that took me so long, but that'll be due after the holiday. Okay, so there's plenty of time to mull it over. And a lot of the questions are really, in some sense, kind of conceptual compared to many of the computational things I've asked you to do in previous problem sets. Okay. Any questions in general about what's happening?
We will be meeting next Tuesday.
Yeah, we'll meet next Tuesday. Just according to the university schedule, their classes meet on Tuesday. I'm not mistaken there, am I?
No.
Yeah.
Okay, good. Yeah, so we'll meet on Tuesday as well. Okay. Right. So we last stated this analog of the mean value property for complex analytic functions, right? We proved this lemma leading up to the maximum modulus principle, which I haven't stated yet.
You did say that you're not thinking about those principles.
I stated that?
Yeah.
Okay.
That's the last thing I have.
Okay, great.
Proof-ish. I don't think we finished the proof.
Yeah.
The last thing I had is there are points z and gamma arbitrarily close to w with the modulus being less.
Yeah, that's what I have.
Right. We talked about how we glossed over how the axioms of the real numbers insist that such a point w must exist, right?
If I remember at the end, you were like, think about it in between classes and see if you can make sense of why they call it what they do. I forget exactly. Like you were like, think about this, and then that was the end class.
Okay, so, good. If you haven't done that yet, maybe do it sometime over the weekend or something. Let's pick up from there though. Let's assume that some point W exists that satisfies conditions 1 and 2 that we wrote down at the end of last time. Okay? So, okay, by property 1 that this point W satisfies, that W, of course, W is some point on our contour gamma, and the continuity of F, the modulus of F of W is equal to the modulus of F evaluated at Z naught. Remember where Z naught is where we attain the maximum of F in this contour, inside this contour. Right? Yeah. Okay. And our last lemma implies that there is a disk D around W where the modulus of F of Z inside this disk D is constant. Remember, we had in the lemma, we assumed that if there was some, if our analytic function F assumes a maximum value at the center of some disk, then it must be constant, right? So this, again, comes from the continuity of F, right? That in some disk, we must have our maximum value attained around W. Yeah.
Do you think you could say the maximum modulus principle one more time?
Yeah, sure. Yeah, sorry, I wish we hadn't finished in the middle of a proof. Let me just state the theorem again, right here, what we're proving. Okay, so here's our setup. If F analytic in D, a domain, and the modulus of F of Z attains its maximum at Z naught in the interior of D, then f is constant in D. Right? Maybe this terminology, this way of saying this is slightly superfluous, right? D, by definition, is a domain, so it's open and connected. So this just, when I say the interior of D, then I just mean it's contained in D. But I say it this way because the corollary will, we will deduce what it means when, that is to say, if we take the closure of a domain where a function is analytic, then the function must attain its maximum on the boundary. And of course, the boundary isn't contained in D because it's open. But I just say the interior of D to emphasize this fact. Right? This is kind of, I state this because we're looking forward.
This theorem just seems so wrong to me. Like it just can't be true.
Doesn't I have no idea what was that?
Yeah, right.
Counterintuitive.
That's exactly. This is what people mean when they say analytic functions are rigid.
And
They're determined very, they're constrained very tightly by any number of conditions. Yeah.
when we say attains its max, do we mean like a global maximum, or do we mean its maximum in the domain?
In the domain. Right?
Wouldn't it mean that?
Wait, yeah, could you, where is this going wrong? If you say f of z is z squared, and then a domain D would be a disk, or a circle of
Sure, you
radius
can
1,
take, yeah, okay.
or take it to this radius 1,
Mhm.
then the modulus of f of z attains its max at some point infinitely close to 1, if it's an open disk.
Well, it doesn't attain a max, right? Just, it gets larger and larger as you, right?
Oh,
That's the point.
okay.
You can't attain a maximum in a domain if you're an analytic function.
I think we were all thinking like,
Yeah.
does this mean that everything's always constant? Okay.
That's why I was confused.
Yeah, yeah.
Okay.
Is that sufficient? Does that clear things up for now?
Yeah.
Actually, yeah.
A lot.
Okay.
I was thinking, just.
Yeah.
It's
F of
recording
z
like
is
this.
Okay. Right. All right. So, good. Let's see if I can pick up here and not confuse myself or you. Oh. Okay. Right. So by our lemma, we're constant on some disk around the point W, where we attain the maximum, right? Okay. And, I'm sorry, no, the lemma implies that we're constant on the disk. It's constant on D. Which contradicts 2, right? The second property that this point W is supposed to possess, that there are points Z on gamma arbitrary close to W with the modulus of f of z strictly less than the modulus of f of z naught, right? That is to say, we approach W from the other side, right? We should have that, it's the modulus of those points, of f evaluated on those points, is strictly less than the maximum, but we've exhibited that in this disk, we have to attain the maximum everywhere, because our function is constant in this disk D. Because we're contradicting our second axiom that we want W to satisfy. You know, I understand that I'm kind of asking you to take a leap of faith that this depends on the axioms of the real numbers. I don't actually have any prepared remarks for that, but if you're not convinced, we should talk about this later. Okay? But if you take my word for it that the axioms imply that such a W exists that satisfies 1 and 2 from last time, then surely we can agree that this neighborhood D contradicts the fact that W satisfies 2. Is that okay?
Yeah. For the first part, when you have the modulus of f of w is equal to the modulus of f of z naught, how does that follow from what you wrote before by 1 in the continuity?
Okay, so remember that statement 1 that W was supposed to satisfy is that the modulus of f of z is equal to the modulus of f of z naught for all z before W on gamma, right? That is to say, we assume that there's some point where we're no longer at the maximum of the modulus of f of gamma.
Yeah.
Right? Okay, so so this is to say our limit as we approach W are all from the left
Yeah.
Before on the curve gamma are all of the modulus are all the maximum value, right? So we have to, if we can get infinitely close and we're still at that value, we have to remain at that value when we get to the point, if f is continuous.
Do you think you could draw a picture just to point to it?
Let's see,
Like,
okay.
It's a point. So gamma is a curve connecting Z1 and Z2, or Z0 and Z1.
Right, so we're saying that there's some point W where our modulus is at the maximum everywhere on this half-open interval, right? The modulus of f for each point along this interval, along this part of gamma, segment of gamma, the modulus is maximum. So since f is continuous, the modulus of f is also continuous, which means that as we approach this point, the modulus of f of w, we're a constant value.
Is the reason it doesn't have to be the limit from both ways because it's like a parameterization, so you're only coming.
Yeah, exactly.
Okay.
So we have this induced order
Okay.
for the complex numbers that lie on gamma.
Okay, yeah, that's what I was trying to figure out why the fact that it wasn't also that value on the right or on the farther side wasn't an issue. It's because it's like direction.
Yeah, gamma is oriented, right? We
Yeah.
have I failed to draw this.
Okay.
The arrow,
Okay.
right? Does this help?
Yeah.
Okay. All right. So let's see. Okay, so now we're done basically, right? We contradicted 2. This implies Z1 doesn't exist. So modulus of x is constant on D. Oh, sorry. Yeah, I really shouldn't have split this proof up. Let's call this D naught, right? Because D was the name I gave the domain of analyticity in the theorem, right? So because we constructed D naught, we know that we have to be constant on all of D.
You're saying Z1 doesn't exist or W doesn't exist?
Both. The non-existence of W implies that Z1 can't exist. Right? What did we define Z1 as?
Isn't
the ending point?
Okay, so this is to say the modulus of, we assume that the,
It can't be non-constant.
right, Z1 was the point where we defined modulus of f was non-constant along the curve gamma that we drew from Z0 to Z1. Okay. Yeah. So I'll.
Is that on D or in D?
That's in textbooks you'll see either, right? Because it's unambiguous because D is open. So when we say on, we mean any point containing. Like you could, there's no ambiguity of me saying on. It's not like there's a boundary of D. I just mean on points of D when evaluated at points of D.
Just a confusion with the disk D. Like can you be in the disk? Like that'd be the interior of a disk. But if you're on the disk, that means you're.
Well, D was a domain
Okay,
from the
so
start
D-
in our hypothesis,
Yeah, okay.
right?
Different.
And also, oh yeah, sorry. There's an open disk, not a smaller one inside D.
Okay.
These are both open. Okay, so I'll leave this open because there's a lot of questions, I guess. But if you take some time and try to assemble the concepts from last lecture and this lecture, the beginning of this lecture, it should all come together. I'm sorry for the confusion here. But are we okay with this? Okay. So, here's the corollary, I promise you. A function, this might be equally confusing, but at least we're starting fresh here. We can address the issues right away. A function analytic in a bounded domain and continuous up to and including the boundary of the domain attains its maximum modulus on the boundary. Okay, let's take a second to break this apart a little bit, right? What does it mean for a domain to be bounded? Remember, I'm using domain here in the topological sense, or open connected set of C. What do we mean by bounded?
Doesn't diverge off to infinity.
Yeah, or
I guess it's for you have a disk that has a high radius.
there's a open disk centered at the origin that contains the set.
For finite radius.
Right. Yeah. For a finite radius, an open set of C, not C,
Yeah.
not C hat. An open ball around origin in C. Yeah, okay, good. So, you might say, well, if we just assume the function is analytic in some bounded domain, we have no idea what it does on the boundary. It could be undefined outside the boundary. That's why we have the hypothesis that it's continuous up to and including the boundary. That is to say, not only is it continuous on the boundary, but it agrees with the values inside the domain as we approach from inside the domain to the boundary. Okay? So we lose analyticity at the boundary, right? Because we can't approach from every direction necessarily. We may or may not be able to approach from every direction. But our hypothesis says that at least we're continuous up to the boundary. Okay?
And like if we apply the f of z equals z squared to like a disk, f of z, or the modulus of f of z attains its maximum on the boundary of the open disk.
Yeah. Yeah,
That
yeah,
makes
yeah.
sense, yeah.
Yeah, yeah, right. When you look at the values on the circle,
Yeah, it's higher than inside.
then it's higher than the inside.
Always.
Yeah.
And it's
Yeah.
constant by the one.
Does it say that again?
Shouldn't it, the value of that, the modulus of f of z should be constant by that lemma we had, right?
Oh yeah, on the
Yeah,
boundary.
on the boundary.
Yeah, yeah, yeah. So this is the main practical way you'll apply the theorem that we just proved, right? It's like, oh, I have some analytic function defined in a domain. Let me check if it's continuous on the boundary. If it is, then I know that it achieves its maximum on the boundary. This is some souped up analog of the extreme value theorem for real functions on compact domains. And there I use domain in the weak sense of it's the domain of the function. Okay. So let's do an example. Maybe this will help clarify things as well. Let's try to find the maximum value of the modulus of some polynomial, z squared plus 3z minus 1, sorry, minus 1, in the closed disk, the modulus of z less than or equal to 1. Okay. So, how should we proceed here?
Say continuous everywhere because of polynomial.
Yeah, that's a good place to start, right? We know this is continuous in the entire complex plane because it's a polynomial, right? Good. Let's try to come up with some bound. We know we can bound this by, for example, the triangle inequality, right? I can bound this by splitting the modulus function across the sum ends, right? This is what the triangle inequality tells me. Okay, so let's write this down. We know this is continuous since modulus of a polynomial and the triangle inequality tells us that the thing that we're trying to find the maximum of is bounded above by the modulus of z squared plus 3 times the modulus of z plus the modulus of -1, which is just 1. Okay, so by our corollary, we know that the maximum of this thing must occur on the boundary of this region. So in other words, we can plug in z modulus of z equal to 1 here, right? So we know that the thing we're trying to find the max of is bounded above by 5 at least. Okay. So now, how should we go about finding an explicit value of the maximum of the modulus of this polynomial on the boundary?
We just pick a point on the boundary and plug it in.
So, okay, that's the right idea. How can we consider all the points in a systematic fashion? I'm sorry?
Parameter as the boundary.
Parameter has a boundary, yeah, good. I just gave a midterm in Calc 3 on Wednesday, and this is, the essential thing for maximization, optimization problems. You have to consider what the boundary is of, some three-dimensional region, and parameterize it, and find the maximum values with respect to the parameter, and then plug them in. So this harkens back to Calculus 3, if you like. Good. Thank you for saying that. Okay, so find a sharp value of the max parameterized boundary. Okay, well, we know how to parameterize the unit circle, right? Let's just do the easiest possible thing.
What's a sharp mean in this context?
Oh, I just mean to find the actual max, right? Yeah, this might be kind of excessive, but sharp means the closest bound you can get. So the sharpest thing we can get is actual equality here. In general, you can't necessarily compute an explicit value, but yeah, so maybe this is overkill to say sharp, but yeah, if you get into like numerical approximations of functions, this is the term that comes up. The tightest bound that you can come up with is sharp, right? Okay. Okay, so let's just do the easiest thing to parameterize it. Just easy IT for t running from 0 to 2 pi. Okay, so then we can compute, this is, let me just write this down and, I guess this takes some insight to see. And the textbook treats it as like fairly routine. And after you do enough of this type of problem, that becomes true. But let's see what happens here. Let's look at the modulus of our polynomial squared. Right? Why do I do this? Because I know that this is actually the complex function inside the modulus times its conjugate. Right? So I'll just write this computation down and then maybe we'll take stock of what's going on here. Okay, so if we plug in our parameterization here, what do we get? We get e to the I 2t plus 3 e to the I t minus 1 times e to the negative 2I t plus 3 e to the negative I t minus 1. Right? I've just plugged the parameterization in and then multiplied my expression by its conjugate inside the modulus. Okay? So if I multiply this out, what do I get? This, I think this gives me 11 minus 2 cosine of 2t. Okay. So, where is this value the largest? Okay, I skipped a lot of algebra here, right? If I actually multiply this out. And let me give you a word of caution for the next few classes. We're going to skip a lot of algebra so that we can state some more powerful results about integration before the end of the term. Okay, so if this calculation isn't totally transparent at the moment, try to multiply this out and derive this expression. Okay. But in any case, where is this? Note that this in fact should be a real value, and here's a function that outputs a real value, right? Okay, so where is this largest?
Pi over 2 and, or wait, pi over 4?
No, I think you were right. Pi over 2.
It's gonna be cosine of negative.
Oh, so I'm thinking of like, because for t, since it's cosine of 2t.
Or you can make cosine equal negative 1.
Do you want to go? Yeah, so it adds the.
Oh, you're right. No, yeah.
No, you were right.
Yeah.
Yeah, right. It's so which is largest when t 2 cos t is equal to 0, right? Which implies that t is equal to pi over 2, and where else in our domain of parameterization?
It's largest when
It's in,
it's when
2, right? Or negative 2.
right?
Oh, yeah, sure. So well, we want this to be 0, right? So we're subtracting.
We're about
No,
to
we want it
add,
to be
we want
negative
to
2.
have cosine 2t equal to negative 1, so we're adding 2.
If 11
Yeah,
minus
because the negative 2 times the negative 1 is going to be 11 plus 2.
Ah, okay. Yeah, you're right. So I shouldn't say this.
that only occurs in pi over 2, right?
Yeah. Well, in the genuine answer.
Yes. And now we're going
Just
to
do the
Yeah.
first derivative test.
Well, but of course, for minus
Four
pi over 2
sine
as well.
minus pi over
4 sine 2t.
You still get,
Yeah, 3. Is 3 pi over 2 included?
Yeah, 3 pi over 2 works as
Pi
well.
over 2 isn't included in our domain.
Is that what you work? 3 pi
Well,
over 2
it
works.
3 pi over 2 is included in the domain, and it works.
3 pi over 2.
Oh, that's in the
Yeah.
domain.
Yeah. So we get two values for t, right?
Yeah.
Pi over 2 and 3 pi over 2.
Yeah.
Okay. So let's just say that largest when t equals pi over 2 and 3 pi over 2. Okay. So what does this tell us about the maximum value of the modulus of our polynomial?
It's less than square root of 13.
Yeah, no, it's actually square root of 13. It attains that value.
And it's because
That's awesome.
we just found that that's at pi over 2 and 3 pi over 2 on the boundary, the maximum value is there, and it's square root of 13, and the corollary tells this, the maximum value.
That must be the maximum value on the boundary,
Cool.
right? Good. Good. Okay. So this implies the modulus of this polynomial as max value square root of 13. Okay. Which where does that occur?
Hold on.
Not quite.
T plus or minus I. Yeah.
Plus or minus I, yeah, exactly. We plug in the values of t into the parameterization, right? So we get z equals plus or minus I. Yeah, remember the way we parameterize this, t was corresponding to the argument, lowercase r, right? If I say this. But yeah, that, again, I'm being a little vague here, but is it okay with what's happening? Okay, good. All right, so now we can finally move on. Well, before I say any of this, maybe let's check. Oh, we still have time before we take a break. Now we can finally move on to trying to make series developments for analytic functions, right? We finally proved, I forget if it was Tuesday or last Friday, that analyticity implies that we're infinitely differentiable on our domain of analyticity, right? That was a recent result that we proved. So it's kind of a natural question to ask, what kind of implications that has for looking at the Taylor series of an analytic function, right? Which is a power series that has coefficients that depend on derivatives. Okay, and then our goal in this development is, and I mentioned this before, is to be able to give a series expansion for a function which may be non-analytic at a finite number of points, i.e. having some poles in a domain that we're considering, right? And this leads to something that's just like a Taylor series, but may have negative powers of our variable z. Okay? And then we'll basically be able to do term-by-term integration of these series, where we can use the Cauchy integral formula for where we have poles. Okay? Again, it's okay if this doesn't make complete sense right now. I'm just giving you an overview of where we're headed. Okay? But I am going to go pretty fast through the techniques of developing series. Okay? Hopefully you remember some stuff about convergence from calculus 2. Maybe sequences and series. Okay. Well, don't be afraid to ask questions if things aren't making sense. Okay. I'll do my best to answer off the cuff, but I really want to get to the integration results. The developments of these series are just tools. Okay. So, okay, so here's the starting point. Let me ask you, let's start this discussion. What does it mean for a series to converge?
No, I guess we're not going to plus infinity or minus infinity.
Not yet.
So, okay.
We will get to a point where we talk about the extended complex plane.
So if you have a sum from like 0 to n, then it converges if the limit as n goes to infinity equals r.
Yeah, that's right. So we're looking at a sequence of partial sums, right? A series is a potentially infinite sum. And we say that it converges if its sequence of sums, where you just sum up to the nth term, if that sequence, as n goes to infinity, converges. And which is defined by a limit. We actually talked about this back in chapter 2, right?
Can we say that with a Cauchy definition?
So, you mean the definition of a Cauchy sequence, right?
Well, yeah.
Where you get arbitrarily close together. So, that's actually stronger than what we need,
Oh, okay.
right? So we may consider sequences which are not Cauchy, but may still converge, right? So, yeah. It's funny that you say that. So remember we were talking about the distinct formulations of the axioms of the real numbers. One of them is insisting that every Cauchy sequence must converge, right? That you formally add in all the Cauchy sequences, whether they converge in the rational numbers or not. Okay. So we're going to take a broader view.
Okay.
Yeah. Good. Okay. So in fact, maybe broader isn't the right term. We actually want to use a stronger notion of convergence than we typically use or have used previously. This is because of the stringent condition of analyticity. Mainly going to be considering analytic functions. So if we want a sequence of analytic functions to converge to the right analytic function, we want a stronger notion of convergence, of what convergence means.
Like uniform convergence.
Uniform convergence is precisely what we're going to use. Okay, so let me give you the definition of that. So this is something that you don't see so much in calculus 2, so I'm going to be explicit about this. Okay? Okay, so a sequence of functions f sub n of z, where n goes from 1 to infinity, is said to uniformly converge to some function f of z for z in some set t in the complex plane, if for any epsilon strictly greater than 0, there exists every epsilon, there exists an integer n, so that when lowercase n is greater than capital N, we have that the modulus of f of z minus f sub n of z is in our set T. Okay, so why did I pause here and change any to every? Maybe this doesn't even help clarify what I was trying to say, but what I'm asking is, what's the difference between our usual notion of convergence and uniform convergence?
Regular convergence depends on Z as well.
Yeah, exactly. That is to say, this integer n does not depend on z. Okay? That is, we can choose some integer n for every epsilon. Okay? You just have to look at epsilon small enough and then be like, okay, well, past this point, it doesn't matter. I can just choose this single n, and this condition holds. Okay? Okay, let's take a 5-minute break, and then we'll resume. Yeah.
A question on my final project.
Yeah, sure.
Like, for me to even start doing my final project, I have to assume that Laurent series should work. Can I do that?
Yeah, that's fine.
Because like, we'll cover them in class.
Yeah. We'll get to next Tuesday.
Yeah,
because we'll mainly start.
It's like the way you start to do Fourier series, you consider, I guess, a power series formed from negative infinity to infinity.
Right.
Yeah.
Yeah, cool.
Of the 5 classes I'm in this semester, 3 of them have broken clocks, 1 of them doesn't have a clock, and 1 has a functioning clock.
This clock.
Really need some like clock maintenance around here.
Spend enough money at the school, they can't give us some good clocks.
There's like 3 weeks of this class. Every time I would look at the clock and be like, oh, it's not even 2 yet? And I'd be like, oh no. Like, you've done so much with attendance.
Oh, I fully didn't realize for you like a good month. And I was like, oh, well, why am I in this class?
So, other than the rescheduling of when we'll actually have our presentations, does my timeline still seem reasonable to have some, doesn't have to be complete, but some kind of draft by, I think it was the last Friday before classes end, December 3rd.
That's 2 weeks from now?
Yeah. If it's not, we can push that to Tuesday, the following Tuesday, which would be, December 7th. I don't wanna make things, due too close to when you might actually have a final or something. You have to study for things. I don't want to have you worrying about turning something in.
Is the idea that we submit it on the 3rd and then just present that on the 14th, or is it like we submit it on the 3rd, get feedback, change and modify it, and then?
Well, okay, so here's the thing, I think the university doesn't allow me to have anything due, like, I think after the last day of classes, but I don't care if you turn it in, like, just before grades are due, which is, December the 20th.
The paper?
Yeah. So like the idea was to be able to give you some kind of feedback.
Okay.
Yeah. So officially, I have to make it due for some time, but I don't care if you turn it in just before grades are due. I guess the latest it should be is like the 18th, just so you have at least the weekend to like actually read them and evaluate them. But yeah, I think grades are due that following Monday, the December 20th. So anytime before then is fine.
So 3 things we submit, I guess. The presentation we have to present, the homework problems we make up,
Mhm.
and then the paper.
Yeah.
The paper and the homework problems are due, so the paper is due the 18th, you said?
Yeah, unofficially.
Yeah.
Yeah.
And then the homework problems, should we give them out during the presentations?
Yeah, just so
Yeah, so people.
other people have an opportunity to actually try to work on them and submit them if they want for extra credit.
When we're presenting, is it like we get 20 minutes to present, give the homework, do questions, or is it we get 20 minutes to present and then we can like give the homework and do questions?
Okay, yeah, so you'll have 20 minutes to present
Okay.
solidly, and then the homework will just be passed out, or
Okay.
and then I was thinking of allowing 5 minutes for general questions.
Do you want it all in LaTeX?
No, you can write it down however you want.
And should we submit the homework problems to you? Like the solutions to someone else's homework problems to you?
Oh, people will submit their solutions to anybody's homework problems to me directly.
Okay, so
You all will submit the actual problems to me and everybody. You'll send the problems out to the entire class, including me.
Yeah. And if someone wants to do someone else's problems for extra credit,
Yeah, they'll just email me.
email you.
Yeah, or submit it via Canvas.
Should we also send you the solutions to our homework, like our problem?
That would be helpful.
Okay.
Yeah.
So, I mean, if you make them hard enough, maybe I won't know how to solve them.
So we're submitting.
Do we get extra credit if you can't solve them?
I don't think that's worth that much. It's not necessarily hard to make a problem I can't solve.
So we're submitting the solutions to the class, or not to the class.
I'll take
Yeah,
the solutions.
Like,
No, just give me the solutions,
Okay, just-
and then I'll send them out afterward sometime.
Okay.
Just for those who are curious. Okay.
and is it extra credit for doing everyone's homework problem?
No, any.
Any homework.
So what, we have 7 people in the class. I asked you to submit 2 to 3 problems, so we're looking at between 14 and 20 problems. I'll probably just give you like a point on your total homework score
We
per
solve our own
extra problem that you submit for extra credit. It's really just, it's a paltry incentive just to like do the problems, you know. I hope that maybe you're interested enough and have enough time to just think about them, but it's no big deal if you don't, right? So,
Definitely interested. The question is, after all my finals, am I gonna be like,
yeah, it's like, oh,
plan to keep doing math?
yeah, right.
Well, I guess since we don't have a final in this class, like we shouldn't be scarred by anything. So
It's
we
true.
should still be.
Also, I submitted this in the question areas, but I realized in the back of my head, like a month ago, I just told myself I have no final exam conflicts, I'm all good. My other final is on the same Tuesday, 3:30 to 5:30.
Okay.
And so now that we're thinking about extending it, I realized if we do it like from like noon to 3, I'd be fine. But if we do a 1 to 4, I'd probably have to like miss the last person's presentation.
Yeah, yeah. Actually, I have to proctor a final exam at 3:30. So, so yeah. I think I was hoping. I was either gonna have to ask a colleague to fill in for me for the first half hour, or hoping that we could go early.
I'm free that whole day.
Yeah, same.
Okay. Well, you know, I'll look. I'll review the surveys. We don't have to talk about that right now. Let's. But yeah, I hope to settle that by tonight. Right. As long as everybody actually answers. Yeah.
And
Okay.
a quick question. This is not for you as much, but for everyone else. I was reading a bit about quaternions. There's a bunch of group theory involved. Do you guys know like the fundamentals of group theory, or should I just leave that out entirely?
No group theory.
No group theory.
Okay, yeah, that's
Well,
good.
you can put it in if you want. I'm just saying I don't know.
Yeah, maybe that's a pretty tall order to go through like the basics of group theory in a 20-minute presentation, right? So I wouldn't fault you for being a bit hand-wavy there, as long as you get the idea of what a group is across. And I think maybe quaternions are not such a bad spot to do that from, since they're kind of physically motivated in a certain way, right? I don't want to say too much here, steal your thunder. But yeah, this is part of the challenge of this final project, is how do I communicate effectively in a short amount of time, right? So let me know, everybody, how that shapes up for you. If you're having difficulty in compressing things, maybe I can give you some advice for what to cut out. Okay. Okay, good. So, right. So, this is the definition of uniform convergence for a sequence. Of course, we'll be interested in uniform convergence of a series, which is defined by the sequence of partial sums. Right? Accordingly, the infinite sum from j equals 0 to infinity of f sub j of z converges uniformly to f of z on t. I guess I should be consistent with what I said over here for all v in t, some subset of the complex numbers, but you'll see the same thing I just erased in the textbook or elsewhere on. If the sequence of partial sums and what do I mean by partial sums? Just to remind you, sum from j equals 0 to n, s of j of n, of z, sorry. N goes from 0 to infinity. Converges uniformly on t to f of z. Okay. Okay. So series are exactly the same for complex, for analytic functions, complex analytic functions, as they are for real valued and infinitely differentiable functions. Okay, so that is to say, if f is analytic at z naught, then the Taylor series of f around z naught is the same old formula you learned in single variable calculus. I'm making the standard suppression here, right? I say f analytic at z naught. What I mean by that is that I'm analytic in a neighborhood around z naught, an open set, that is to say. And when I say the Taylor series of f around z naught, I mean the Taylor series in that open neighborhood where I know that f is analytic around z naught. Okay, is f evaluated at z naught plus f prime evaluated at z naught divided by, 1 factorial times z minus z naught plus f double prime of z naught divided by 2 factorial times z minus z naught squared plus f differentiated n times evaluated at z naught divided by n factorial z minus z naught to the n, continuing on to infinity. I just put that in there for show. Okay. Right. So again, up until last Friday or maybe Tuesday, this seems like less hypotheses on a complex function for when I can write down a Taylor series like this. But we showed that all the derivatives of all orders exist for an analytic function in a neighborhood of analyticity. Okay. So here's the main theorem. There was a question about this earlier in the term, and I kind of made some allusion to the solution. Joe, I think it was you who asked it. Yeah, the difference between holomorphic and analytic, right? Historically, well, I was looking around on the internet before class today. Different sources say different things, but historically, according to what I've heard, historically, holomorphic meant having a convergent Taylor series in a neighborhood, and analytic meant just complex differentiable, as we've developed throughout the term. These two concepts are the same. They coincide. Holomorphic and analytic are synonymous. That's a major theorem of complex analysis. Okay, so without having defined the term holomorphic, let's prove that theorem. Okay? Yeah, it's funny. When I was an undergraduate, I took complex analysis with a professor who was in his 70s. And, he made this big deal about showing that these two concepts are not the same, but for example, in our textbook, which I think was published in the 80s, you know, the term holomorphic is almost nowhere to be found, right? So, historical note. There used to be this thing, holomorphicity, that is the same as analyticity. I guess maybe analytic one because it's easier to say. Okay, so if F is analytic,
Is holomorphic and analytic for real valued functions the same, or no?
As far as I know, holomorphic is something that has historically only been applied to complex valued functions. This would be, now that it's too late since everybody's decided, but this would be a great final project, distinguishing the difference between complex analytic and real analytic. Okay? So real analytic is essentially means the same thing as complex holomorphic means. You have a convergent Taylor series someplace, and this makes a real function rigid in the same way as we were describing before. A real function which converges to its Taylor series in some neighborhood has all these nice properties that we've described about being determined very tightly by its values on the boundary, say. Okay, so there's a lot to say there, but I'm not going to do it justice. But maybe look into that sometime. What it means to be real analytic, and compare that with the notion of analyticity we've developed here. Okay, so let's say that if F is analytic, in this set, the open ball centered at Z naught of radius capital R, then the Taylor series of F of Z converges to F of Z for all Z in this open disk. You can say something even stronger. Furthermore, the Taylor series of F converges uniformly to F of Z on any closed subdisk modulus of Z minus Z naught is less than or equal to R prime less than R. Okay, so that is to say, we can't necessarily say anything on the boundary of the domain of analyticity, but if we look at any closed sub-disk of the domain of analyticity, we converge uniformly everywhere there. Yeah?
Can I take a guess like what we're going to do with this?
Sure.
If it converges uniformly to F of Z on any closed subdisk, if you take a smaller and smaller subdisk, you should still contain the information of F of Z. So couldn't we break up functions of poles into parts that contain just Taylor series centered around very small disks around them?
Yeah, that's exactly what we'll do when we get to chapter 6, right? We'll express our functions as convergent Taylor or Laurent series and look at their series expansions near each pole and integrate those series rather than the function itself. And then we can use all our nice results about the Cauchy integral formula and such. Yeah, that's exactly what we'll do. How about for proving this theorem, which I think it's a bit tedious, but I think it's worth seeing. So we'll do that next. But what do we think for how we'll prove this? Any guesses? Well, I'll give you a very vague hint. We're going to use the machinery that we developed in chapter 4, right? The Cauchy integral formula. The Taylor series depends on the derivatives of f, which is an analytic function. We'll express those derivatives as integrals, and then bound the integrals, right? The thing that we do for all the integral theorems that we prove. Yeah?
But we know from our previous theorem that all the derivatives are, they don't attain a maximum inside the disk. Right? So
Yeah?
this function uniformly converges to f of z if... Oh, I'm sorry.
No, don't be sorry. Yeah, maybe we can reconcile your thought as we go through the proof. Yeah. Okay, so I'm just going to prove this strong thing that we have uniform convergence on any closed subdisk of the domain of analyticity. And then maybe for the last problem set, I'll ask you to take the final step and show that this implies that. Or maybe you see that right away. But that's okay if you don't.
We just did the limit.
Yeah, basically that's essentially the idea. But yeah, so let's just prove the strongest thing. Okay? So let's let C be the circle centered at Z naught of radius r plus r prime divided by 2 for some closed subdisk of radius r prime, just like in our notation for in the statement of the theorem. Yeah? Okay, good. I think I have enough time to actually complete this proof. Let me draw you a picture. Here's our complex plane. Here's my point Z naught. Okay, let's say here's my domain of analyticity. Yeah, and let me take some closed subdisk of radius r prime, and then my circle C will be something of radius, the average of r and r prime. Right? this here. R plus R prime divided by 2. Okay? So, oh, sorry, if I want to use the Cauchy integral formula, I should orient this intermediary circle C. Okay, so let's label this C, and let's give it positive orientation. Okay. So, sorry, put this here, so it's less in the way. I'm gonna try to keep this on the board for the entirety of the proof. Okay, then, by the Cauchy integral formula, what do we have? F of z is equal to 1 over 2 pi I times the integral along our circle C of f of zeta divided by zeta minus z d zeta. Okay, here's the key step that really this is the hard thing to come up with, right? What we're going to do is we'll manipulate this integrand to get a geometric series, which we have an easy way to test the convergence of, right? You remember how to test the convergence of a geometric series?
1 minus the,
N over 1 minus R.
Yeah, exactly. That's exactly the formula we'll use, and I'll state that in a lemma as we progress. I realize now I'm definitely not going to finish this in 13 minutes, but we'll get at least halfway there. Okay, so manipulate the integrand to get a geometric series. Okay, so here's what I'll do. I'll specifically just forget about f for a minute. Okay, so let me just start by looking at 1 over zeta minus z. Well, this is the same as 1 over zeta minus z naught minus z minus z naught. Okay? Seemingly superfluous manipulation. But I can also say that this is equal to 1 over 1 minus z minus z naught divided by zeta minus z naught times 1 over zeta minus z naught. Okay, what am I doing here? This is the formula for what a geometric series converges to with, I forget what you call it, the thing that you raise the power to, the ratio, yeah, the ratio equal to this. Now, let's refer back to our diagram. Remember that zeta, by the Cauchy integral formula, zeta is on the circle C, right? And z is somewhere inside radius r prime that we're looking at, right? So when we look at the ratio of this distance to this distance, we get something that's has modulus less than 1, right? Because this length is smaller than this length. Yeah.
Why does Z have to be inside of R prime instead of just inside of C?
Let's see. Oh, so what was the statement of our theorem? Remember, we're trying to prove that the Taylor series converges uniformly on any closed subdisk. So actually,
Oh, right.
Z can go up to R prime,
Right, okay.
but not beyond. We're trying to prove that the uniform convergence within and on this closed subdisk. Okay, good. Okay, so note the modulus of z minus z naught divided by the modulus of zeta minus z naught is strictly less than 1, which implies that this expression is equal to, we'll just expand this out into the geometric series that this converges to. What do we get? 1 plus z minus z naught over zeta minus z naught plus z naught divided by zeta minus z naught to the power n. Oh, shouldn't put my close bracket there yet. Plus this this basically error or remainder term, right? Z minus z naught divided by zeta minus z naught to the end divided by 1 minus z minus z naught divided by zeta minus z naught close bracket, right? So this is the geometric series. Yeah.
Where does the error term come from?
This is the lemma.
Oh.
So, yeah, good. But let me not forget this term, right? Times 1 divided by zeta minus z naught. Yeah.
I don't know if this is important, but I think it should be n plus 1 on the error term, right? Because you're starting from the...
Oh, yeah, you're completely right. I put n here. Yeah, that's good. Thank you. Okay, so let's remind ourselves where this error term comes from. This is a general fact of geometric series, right? Oh, I erased my picture. Damn it. Since lemma, what should I say here? Maybe I actually don't have to state this separately so formally. I want to get through at least the justification of this. Since 1 over 1 minus c minus the nth partial sum of some geometric series is equal to c to the n plus 1 divided by 1 minus c. Okay? With c here equal to c minus c naught divided by zeta minus c naught. Okay. Just really quickly here, let's justification. If I take 1 minus c times the nth partial sum of some geometric series, what do I get?
1 plus c, 1 minus c and then minus 1.
Yeah, exactly.
C to the n plus 1.
Yeah, right. 1 minus c to the n plus 1. Right?
Yeah.
Multiply all these terms by 1, you just get the same thing. And then multiplying by negative c switches the sign and shifts the power up 1 for everything. So you get all cancellations except for the first term and the last term times c. No, sorry, minus c. Okay? Good? So, if we just rearrange this slightly, what do we get? We get that the nth partial sum is equal to 1 divided by 1 minus c minus c to the n plus 1 divided by 1 minus c, right? I've just divided by 1 minus c both sides and split the difference. Okay? So this implies in turn that c to the n plus 1 divided by 1 minus c is equal to 1 divided by 1 minus c minus the nth partial sum. Okay. And take the limit as n goes to infinity, right? So what am I doing here? I'm taking the nth partial sum and subtracting that from some quantity. And I have an expression for that. Right? So if I take the limit and it turns out to go to 0, then I must have that this is equal to the limit of the partial sums, the sequence of partial sums, right? So the limit as n goes to infinity for the absolute value of c, or sorry, the modulus of c less than 1 goes to 0 here, right? Because the modulus on the numerator gets smaller and smaller and smaller, and the denominator stays the same since there's no factor of n in the denominator. Okay? So we take the limit and the left-hand side goes to 0. Okay? So that is the justification for this equality. Right? This is just our error term, right? Where C is the ratio of the differences of Z, Z naught, and zeta, zeta naught. Zeta, Z naught. Okay. Good. I probably could have organized this better, but I hope it's clear what's going on.
And there would be no error term if you took n goes to infinity, right?
Yeah, right. But we get the error term because we're looking at a finite, a particular partial sum, the nth partial sum. Yeah, that's the answer to your original question. Where does the error come from? The fact that we're looking at a particular partial sum. Okay. Okay, so we're actually doing okay. We might get more than halfway through the proof of the theorem. Okay, so then by the generalized Cauchy formula and linearity of contour integrals. We have the following. F of z is equal to 1 over 2 pi I times the integral along C of f of zeta divided by zeta minus z naught d zeta plus z minus z naught divided by 2 pi I times the integral along C of f of zeta divided by zeta minus z naught squared d zeta. Right? Remember what we were doing? We used the Cauchy integral formula once to express f of z as an integral. Now we came up with a a geometric series expression of our integrand. So I plugged that geometric series expression into the original contoured integral we have, and then split it up by linearity to get an infinite sum, where the terms are integrals for each term of the geometric series. Right? Okay? So, well, I guess I should write more terms of this to make it clear. Z minus z naught to the n divided by 2 pi I times the integral along C f of zeta divided by zeta minus z naught to the n plus 1, right? The zeta plus this different term that comes from our error term, right? The integral along C of f of zeta divided by zeta minus z times z minus z naught divided by zeta minus z naught to the n plus 1. d zeta. This is from the error term of the geometric series, right? with series, right? Now all we have to do is bound this integral and show that it goes to 0 as n goes to infinity. Okay. Good. Have a good weekend, and I'll see you on Tuesday.